Welcome back to the Explainers. So glad you're here. This explainer is proudly brought to you by Forge College. Now, in our previous lesson, we laid down the foundational concrete for Anchor testing, really just getting a feel for the environment. But today we're taking the next massive step in our journey from EVM to SVM. We're going to tackle exactly how you take your existing Hardhat knowledge and map it directly to this new Solana ecosystem. Let's dive right in. So, are you ready to translate your Hardhat test suite? I like to think of this transition as the engineering retrofit. We're essentially pulling out that old familiar EVM machinery, those implicit gears you've relied on for years, and installing brand new, highly explicit SPPM plumbing. Now, it might feel a bit manual at first, I know, but once you see how much control you actually have, you are absolutely going to love the precision it offers.
Section 1. The Hardhat to Anchor Dictionary. Translating your engineering blueprints.
All right, let's look at how we handle user accounts. Over in Hardhat, you grab your tools using the trusty old EVM wrench, right? That ethers.getSigners function. It practically handed you ephemeral signer objects out of thin air. But in Anchor, we're swapping that out for the new SVM Hydra Spanner. To actually get accounts now, we explicitly use Keypair.generate to create brand new cryptographic identities. And for our default local test grid signer, we rely on provider.wallet. So no more ephemeral magic, it's all explicit cryptography from here on out.
And here's how this shift applies when we actually want to trigger a contract. You're probably super accustomed to typing contract.connect.signer.method. Well, in Anchor, that translates to program.rpc.method. The absolute crucial point here is that Anchor methods require you to explicitly draw the wiring. You can't just connect a signer and hope the Ethereum virtual machine magically figures out the state routing for you. On Solana, you have to list out the exact accounts and signers in a dedicated accounts object for every single invocation. It's totally explicit.
And this brilliantly illustrates the philosophical shift in how we actually verify our work. Back in Hardhat, checking state usually meant simply reading return values from public getters. Expect value.to.equal x. But in the Anchor ecosystem, we take a much more grounded approach. We explicitly fetch the complete on-chain data container using account.fetch, which deserializes the data for us, and then we assert on those specific fields. It is a highly deterministic, incredibly reliable way to verify your state changes.
So here is your master patent diagram. This table summarizes the entire translation mapping we just went over. Honestly, I'd highly recommend keeping this cheat sheet handy for your daily retrofit work. Just to recap, for invocation, we map our contract methods to program.rpc. For account access, we move from simple getters to fetching. And for deployments, well, instead of those complex fixture scripts, we just utilize the Anchor workspace, local airdrops, and explicit account creation right inside our tests before each hooks.
Section 2. Rewiring state changes. Building the new sequence.
Okay, so every successful state change test in Anchor follows this exact new 5-step workflow. 1. Set up the provider to connect to the network. 2. Generate a keypair to hold your new state. 3. Airdrop funds to pay for the space. 4. Make the RPC call to trigger the logic. And 5. Fetch and assert to verify it all worked. Each piece of this plumbing is absolutely essential, guys. If you skip even one, the machine simply won't start.
Let's zoom in on step 1, the Anchor Provider. Think of the provider as the main power source that lights up your entire local testing grid. It manages the connection to your local validator and automatically binds your default wallet right to your transactions. So grabbing AnchorProvider.local is quite literally always going to be your first move.
Now, unlike the EVM's implicit contract storage, where deploying a contract just automatically hands you a database to write to, Anchor requires explicit on-chain data containers. You have to actively create an account. Usually, you're doing this by generating a new keypair or deriving a PDA, and that specific account will physically hold your program's state. It's a totally different mental model.
Section 3. The counter schematic. Let's look at a concrete engineering example.
Right, before we write any execution logic at all, we need to pull the right parts from our inventory to scaffold the initial test setup. First, we need our local Anchor provider to power the connection. Second, the counter program workspace, which lets us dynamically resolve our compiled program without manually hard-coding any addresses. And third, a fresh key pair to serve as the physical address for our counter's memory.
And here's a pretty fun quirk of Solana plumbing. Even your dummy test accounts need a quick airdrop of LAN ports before you can actually turn them on. Since Solana charges rent for storing data on-chain, you have to call request airdrop, followed by confirm transaction, to fund that fresh key pair. It's basically paying the network's tolls so your account is actually allowed to exist during the test.
Next comes the initialization instruction, and this perfectly illustrates that strict wiring I mentioned earlier. To initialize the counter, our counts object has to explicitly map the counter to our new Keypair's public key, map the user to our provider's wallet, and, get this, we even have to physically pass in the system program. Account ownership and execution privileges are just brutally explicit here. No assumptions allowed.
Once that setup is all wired up, we trigger the actual state change. We simply execute await program.rpc.increment and pass in our counter account. Now, what's really beautiful about this in the Anchor testing environment is that it assumes the transaction is confirmed by default. The moment that promise resolves, your local validator has successfully processed the transaction. Literally zero manual polling required. How great is that?
So the crucial point of the final step is verification. We fetch the deserialized data using program.account.counter.fetch. Now, because Anchor handles the binary translation behind the scenes, numeric fields usually return as big number, or BN, objects. We simply convert it using .toNumber and assert that it equals exactly 1. And boom, our retrofit was a complete success.
Now, before we wrap this up, we've got to talk about test isolation. Back in Hardhat, you probably used those implicit global snapshot and revert commands to sort of magically reset the validator state between your test blocks. While on Solana, we're ditching those global validator state snapshots. Instead, utilizing fresh accounts is the absolute key to perfect test isolation and CI compatibility. You just generate fresh key pairs and do local airdrops for every single test. Trust me, it is infinitely more reliable.
Section 4. Final blueprints and next steps. Wrapping up the retrofit. I want you to burn this golden rule of Anchor testing into your brain like a sacred engineering maxim. Make accounts explicit and prefer deterministic state checks. Honestly, never assume the network knows what accounts you want to use. Just list them all. And always verify your program's behavior by directly fetching the deserialized on-chain state.
But listen, porting your tests is really just the beginning. The real question is, when your brand new SVM engine misfires, do you actually know how to look under the hood? Well, we'll be tackling exactly that in our next lesson on debugging Solana programs. I do want to remind you that this explainer was brought to you by Forge College. Be sure to visit Forge College to access deeper development resources and explore a whole variety of other cutting-edge Web3 topics. You've got the blueprints now, guys. Go build.